Good morning, everybody. Welcome to our webinar on climate change and building resiliency. My name is John Holland. I'm the Chief Development Officer of Pinchin, calling in from Vancouver. And I'm joined by our two panelists today, Dr. Ryan MacDonald from the University of Lethbridge and Gord Rajewski from Pinchin's Edmonton office. This webinar is part of our continuing practice innovation series where we share our technical and business landscape lessons with our community through the pandemic and beyond the pandemic, we anticipate. This is where we share what we've learned and what we see evolving with you to promote more broad debate on where our society is going and what we can all do collectively to mitigate some of the risks and issues that we come up with. A recent study from the Insurance Institute of Canada reported that major weather impacts are doubling every 5 to 10 years, and weather claims in Canada are predicted to increase of up to 5 billion in the next 10 years. This, of course, represents a massive risk of compromised or uninsurable assets and a redirect on how we design buildings infrastructure to contemplate future impacts. Our own University of Toronto was the first university in North America to establish a building resilience research capacity. And in 2016, the university collaborated with BOMA Toronto, and they led a study to investigate what building and infrastructure can physically carry in the event of an extreme shock to its operations and the practical limits of densification and space optimization. And the outcome of this study was a collaboration that contributed to the development of a new United Nations standard on smart city connectivity that will enable resilient communities. So thank you to BOMA and to the University of Toronto for your leadership in that area. Next slide, please. So a few notes for Zoom webinars, which I'm sure you're all aware of. Get comfortable, set your audio volume. If you could all raise your hands so that we know we can be heard. We have a couple of functions that we use. The chat function is for you to raise technical issues that may come up. You can't hear us, the slide isn't advancing. The Q&A is for technical questions that we'll try to moderate through the session. I don't believe we have any polls today. We have polls in some of these, but also any technical questions you have, please use the Q&A. And either the speaker will answer them at the time or we'll try and moderate those at the end of the session. We anticipate about an hour today. Thank you. And next slide, please. So we have two speakers today, Ryan MacDonald and Gord Rajewski. First speaker will be Ryan. Ryan is a senior hydrologist with MacHydro. Ryan's been conducting research and working in the hydrometeorological science area for over 11 years. He's a research consultant and an adjunct professor in the Department of Geography at the University of Lethbridge in Alberta. And his work focuses on hydrological processes, modeling, and freshwater ecosystems. He's worked throughout Western Canada, and Ryan is a technical advisor for the Columbia River Treaty, providing guidance to federal, provincial, and First Nation governments. He's also led several watershed-scale assessments looking at the interface between human land use, climate, and the natural environment. In lieu of a fee for his presentation today, Ryan has kindly donated an honorarium to the Gord Downey and Cheney Wanjak Fund in support of our First Nations people that attended residential schools. So thank you for that kind donation, Ryan. The second speaker is Gord Rajewski. Gord is the National Practice Leader, Building Science and Sustainability group at Pinchin. Gord holds an honours diploma in Building Construction Engineering Technology from the Northern Alberta Institute of Technology. He's a registered engineering technologist and has more than 35 years of building envelope and roof consulting experience. Gord has undertaken projects throughout Canada and parts of the US and even one assignment in Africa. Gord provides senior management and key technical support for all building science and sustainability projects at Pinchin. And so we're glad to have both these presenters on our session today. Thank you both for preparing for this. Thank you to all of our backup team, Kaylee and Ruth, for being part of the process. And with that, I will hand the podium over to Ryan. Thank you. Ryan, if you can hear me, you're muted.
All right, can you guys hear me now?
Yes, we can. Thank you.
All right, thank you. Yeah, good morning, everyone. My name is Ryan MacDonald, and yeah, I'm going to chat with you today a little bit about climate change and building resiliency. So just to sort of start off and give us a bit of perspective here, you know, we've now developed as a kind of scientific community this new term called Anthropocene. And in geologic terms, we have all of the different, different periods in time. And we've invoked such a large effect on Earth and on the atmosphere that we've actually started to term a new geologic term, and we're a new geologic force on the planet, and it's driven by humans. And climate change is a really good example of that Anthropocene idea, and it really is a planetary scale effect that we're having. So when we think about the things we can do to Earth, the things we can do to the atmosphere, we have a really big force on the climate and on Earth in general. So this idea around the fact that we can actually shape the way that society, the way that ecosystems respond, the way that our atmosphere is responding is a really profound thing. So just giving us a bit of perspective, and also related to that, it's not all humans on Earth that are driving this. So around 1 billion people ish live with seemingly unlimited access to fossil fuels. Around 3 billion people live with this huge lack of fossil fuels and struggle to even cook food. So there's this huge discrepancy in the global population, and I hope today I'll be able to highlight this discrepancy is both a challenge and an opportunity, in that we have a huge challenge in front of us, and we have also a really big opportunity, and that's this whole idea around resilience and building resilience for our communities and building resilience for, I guess, humanity in general. So just starting off there, what's the science telling us about climate change? So there's been a lot of different studies and a lot of different news articles, etc., put out over time. Really, that there is consensus. So there's the vast majority of the science, the good science that's looking at this. There's a consensus on the fact that the climate is changing and we're causing it. And that consensus goes beyond climate scientists. It stems into the economic sector, it stems into social sectors. It's not just the climatologists that are looking at this. So number one is we have consensus on this as a scientific community. We've developed these international bodies of researchers and experts in these disciplines to evaluate that. Something called the IPCC is a global science body that synthesizes all of this work and does a lot of work relative to climate change. And what are we seeing? We're seeing things like ocean acidification. I'm I guess an avid scuba diver, or at least I used to pre-COVID. But even in my lifetime, I'm 40 now. In my lifetime, I've observed bleaching of coral reefs. That's pretty profound for me, being someone that enjoys being outside and enjoys being in that environment. And when we can observe these changes over relatively short periods of time, we know that they're happening. So things like ocean acidification are happening, sea level rise. I'll talk today a lot about drought, fires, the different types of storms that are relevant to us, floods. Really important to all of this is the fact that we're losing our biodiversity on this planet. We're seeing a lot of species disappear. We're seeing all sorts of things go on in kind of the natural environment. And what this is from is essentially the natural rate of warming is around 4 degrees Celsius over 5,000 years. And what we're seeing is, that same amount of warming over a much, much shorter time period. So over the past 100 years. And I'll talk about this today as well. We look at the poles, they're warming much faster and to a much greater extent. Weather extremes are becoming more variable. Things like crops are becoming more sensitive. And we're seeing things like human health issues pop up, both in terms of heat waves, air pollution, and things like diseases. So these are all relevant things to us. And I guess the main point of this slide is we have agreement on what is actually occurring. So to put some numbers behind this and kind of give us a bit more perspective, we expect in the next 15 years that we're likely, if we kind of go down the road that we're going down right now in terms of our greenhouse gas emissions, we're likely to exceed the threshold for dangerous climate change. So we're likely to emit enough carbon dioxide and other greenhouse gases to the atmosphere that we're going to exceed this threshold for kind of dangerous catastrophic effects. Over the next 35 years, we may see this 2 degrees Celsius warming, which a lot of the climate literature is looking at as almost like a threshold to which we will start to see very dramatic ecosystem responses, sea ice loss, all of these different kind of factors. We will start to see that at around 2 degrees Celsius. And that then subsequently translates into about 5% chance of catastrophic changes. And that 5% may seem like a relatively small number, but that's catastrophic changes. That's in addition to things like floods, intense storms, huge droughts. We may see some pretty radical changes into the future. So with that, we really need to start thinking about, so how do we, sound is fading in and out. Would be beneficial to actually see the speaker. Do you guys want me to share my Kaylee or Gord, you guys there?
Keep going, Ryan.
Yeah, keep going.
I can hear you fine. I can hear you okay so far. So maybe it's recipient's audio.
Sounds good. You can share your video if you like. Apparently, I can't share my video because the host is stopped. Anyways, I'll just keep going. So what's going on in our atmosphere? And this is based on measurements. So we have pretty good measurements of what went on over the last several thousand years, actually hundreds of thousands of years. We understand what the carbon dioxide levels were in our atmosphere. And we look at this graph. This graph is from thousands of years before today, and today in this case, before 1950. So if we look a long ways into the past, we can see the natural variability of carbon dioxide, in previous times was around 300 parts per million in terms of a maximum. And that was kind of, we do see as kind of long-term variability. I'm not going to get into how we measure this, but what we see is this long-term variability is dwarfed by what we see currently. So we're currently seeing around 415 parts per million of carbon dioxide in the atmosphere. And for those of us that took the greenhouse effect in high school, that has a pretty big greenhouse effect on what's going on in the atmosphere. So as we increase the carbon dioxide in the atmosphere, more of the Earth's energy is being trapped. So that's what's going on, and that's really what is driving this warming. And we can measure it. So there's this really nice website that NASA's developed. I'll just step this through time, and this is looking at the temperature difference, and these units are Fahrenheit, but just concentrate on the blue and the red. And we see kind of variability across Earth over a long period of time, and this was only measured since just pre-1900 all the way up to 2020. But what we're seeing in this map is kind of a shift of warming and cooling of Earth over a relatively long time period. And as we start to move into kind of when humans were on Earth, or humans were actually affecting, I guess, the climate of the Earth, we start to see more and more of the red occur over time. And what that is essentially more and more warming. And we see this kind of highlighted, look at here, 1970. So now we have the Industrial Revolution. We start to emit more and more carbon dioxide. And now we start to see the effects of that carbon dioxide. So the map is no longer mostly blue, it's now mostly red. And what we're seeing is most of that warming is actually occurring in the northern hemisphere, and most of that warming is actually occurring in the poles. So this is what we expect, is that kind of dramatic warming of the north. And that's really important for us here in Canada, as we can see dramatic changes in our climatic system and our weather patterns. Oops. So what has this done? So we've actually seen some it's not counterintuitive, but we're learning all the time. So we've built these models and these climate change models that we as a discipline often use, and they're changing over time. We're learning more and more about the physics of the climate system itself. And one of the things that's really profound, I think, for Canada and I guess the globe is this idea around positive feedbacks. And what we found is that the previous climate models weren't doing a very good job of kind of replicating. We weren't getting the physics right. And one of the really key findings was wow, the sea ice actually had this very positive feedback loop. So as we lose more sea ice, we reduce the albedo of Earth. And the albedo is essentially the reflectivity of Earth. And as we lose, more and more snow, and ice, sorry, we start to reduce the albedo. So we reduce the amount of reflective surface on Earth. And what that does is it has this positive feedback. And positive feedback means that we have increased and accelerated warming. And that's why we see what we're seeing in the north is this accelerated warming effect. And what this does, it just feeds back on itself. So at a certain point, you can't actually stop it because it's a feedback cycle. So that's really important to consider, that we've had substantial sea ice loss. And what does this do? This ultimately, we've got the effects on climate, but we've also got the effects on humans. And here's another graph produced by NASA, and this is sea level height variation in millimeters over time from around 1993 to the present. And what we're seeing is around a 3.3 change in terms of sea level rise, 3.3 millimeter change per year. That may not seem like a lot, but if you accumulate that over a long period of time, you can see that a large population a large part of our population actually resides within sea level. So that starts to displace communities. And we've done a bunch of modeling all over the world to understand what that would do. And billions of people would be displaced as a function just of sea level rise. Inverse to that is I guess we have rising water levels, and we also have this really, really dry system that's occurring. It's a very variable system. Here's some work done fairly recently in the United States looking at cumulative forest area burns. And what they've done is they've attributed wildfire to climate change and without climate change. So what we see is that we've seen much more wildfire as a function of climate change. And recently in the Western United States, we've seen some massive fires, and billions of dollars in damage each year occur as a function of these fires. And in British Columbia and other provinces, we're likely to see quite dramatic changes in wildfire behavior and wildfire intensity. Accompanied with wildfire, we also have drought, and large parts of North America are agriculture producing areas. And this is some work done by NOAA out of the Princeton University. And they looked at this thing called probability of drought index. And what it's looking at, this is a long-term simulation, so looking at around 100 years from when the study was done. And what they're showing here is the -6 on the brown is severe, and the +6 on the blue is less severe, or is good. And what we see is this very severe shift, excuse me, over sort of the United States into southern Canada, large parts of Europe, South America, Asia, all over the world. We're likely to see these, much more severe droughts. And for Canada, this is really important. So southern Canada produces, southern Ontario, Saskatchewan, Alberta produce a lot of our food. And the risk to food production is very, very significant. This also impacts water security. So as we see more and more drought, the food production plus the changes in water security pose a pretty big challenge. Looking at kind of farther east in Canada and other parts of North America, we also see this increased intensity, frequency, and magnitude of hurricanes. So with sea level rise, warming of land masses, and warming of the ocean itself, we see much, much more energy in the system. And this increase in energy actually produces much more intense hurricanes and tropical storms. So these hurricanes and tropical storms there's been a ton of work done on this because it's such a big issue. With really high certainty, they're predicting that major storms like hurricanes and tropical storms are likely to, very likely to increase in terms of magnitude and frequency into the future. That's pretty scary for those coastal communities in the Atlantic. So major damage and risk to many, many communities across the globe. Similar to hurricanes, we also have flooding, so we're pretty familiar with flooding. I personally do a lot of work on flooding, and one of the bigger ones we recently did work on is Calgary in 2013. Some folks in 2003 put together this really nice, although it's kind of tricky to understand and read through, but this really nice kind of diagram that looks at this kind of cumulative effect of flooding and what we've done to increase our risk related to flooding. So we've done a bunch of things. We've climate change is there that we're talking about today. We've also changed the land use, so changed the landscape. We've modified rivers, and we've decided to live near rivers in many parts of the world. Especially in North America, we have this idea that we need to live right near rivers, and large communities are built on rivers. This is kind of a complicated matrix, but really the global change aspects talked about in that kind of top row there are really things that we're doing that make our interaction with rivers and flooding very risky. So we have, as a function of climate change and all of the other things that we do on the landscape, we have high probability of extreme flood events into the future, and that poses challenges for us. Luckily, with those challenges, so I started off today's talk talking about opportunity and kind of where we're at as a global society. About 1% of the world's richest people cause more than double the carbon dioxide emissions of the poorest 50%. So what that ultimately means is we, as a fairly developed world, we have an opportunity to help out the rest of the world. And what I'll end the talk with today is a little bit of discussion around how that might be achievable. So we've got today's workshop really is on building climate resilience. And there's two pieces to resilience. There's mitigation and adaptation. Mitigation is really action to reduce emissions that cause climate change. And adaptation is managing the risk to climate change. So the Pinchin folks today will talk about the adaptation piece. And I'm going to talk a little bit about the mitigation piece. So this includes things like clean energy, different types of transportation, different types of strategies to help us get past where we're at right now. And when we talk about wanting to implement strategies or mitigate climate change, really we have, I'll talk about this in the next slide, but really we're trying to bend this curve. And when I talk about this curve, I mean the carbon dioxide curve and the other greenhouse gas emissions curve. So the strategies that we have available to us are things like renewable energy, changes in pricing of carbon, environmental protection, the idea that inaction results in pain for us, opportunities that we can kind of go after as a society that make it actually, that make the challenge kind of fun as a society. So there's been some work done from the University of California that's looked at these 10 solutions to bend the curve. We have science, which is in the middle, that's really driving kind of what goes on and how we can go about mitigating climate change. We also have things like societal transformation, governance. The economic sector has a huge role in markets and regulation. We have the technology sector that's really been improving technology a lot lately, but it plays a really important role. And then ecosystem management, so promoting healthy ecosystems. These kind of 10 key pillars really help us to kind of frame ourselves around how might we deal with this issue. And when I talked about that curve is really what I'm showing here. And there's a few levers that we can pull as a society. So the curve is showing degrees Celsius in warming over time from 1950 to 2100. And if we don't do anything, that curve just kind of increases over time into that red zone that you see. If we only mitigate carbon dioxide, you can see that we start to bend that curve and keep it around 3 degrees Celsius, by 2100. If we implement strategies that mitigate short-lived climate pollutants, so things like methane, we can also change that curve, and we kind of come up into the same place as 3 degrees Celsius by 2100. But if we implement strategies that actually bend that curve significantly by reducing carbon dioxide emissions and these other atmospheric pollutants, we can keep ourselves below that 2 degrees Celsius benchmark that we're trying to get to. What does that look like? So business as usual is shown in A, and greenhouse gas emissions is shown in B. And what this is 2 different maps looking at the change in air temperature. And the 50th percentile, or kind of the median value, is shown in the bigger map. And if we are to kind of go about business as usual, so shown in A, we see a much warmer Earth, or much warmer, I guess, Canada, by the end of the century. If we are to mitigate and actually implement climate change mitigation measures, we see that we can actually reduce our warming quite substantially. And these are model simulations to show us that if we are to implement these strategies, we can go about reducing greenhouse gas, or we can go about reducing greenhouse gas emissions and subsequently reducing the effects on air temperature. And one thing I want to point out is the green in this case is around that 2 degrees Celsius. So that 2 degrees Celsius, as I mentioned at the beginning of the talk, is the place where we start to see significant change. So if we implement carbon dioxide and other greenhouse gas emissions reduction strategies, we can keep ourselves at that level. If we don't, we're surpassing that by a large magnitude. So how do we go about doing that? And I'll talk about a few Canadian examples. Wind energy. So investing in wind energy and producing wind energy is a very good thing to do. Wind turbines. I spend a lot of time in Southern Alberta, and they're popping up all over the place. Southern Alberta and Saskatchewan are really the hot spots, I guess you could say, for this type of technology. We have access to grids that feed into the states, access to grids going west if possible, or if they're implemented. And wind energy is a fairly reliable and practical solution to producing sustainable energy. Solar. So again, Southern Alberta, Saskatchewan, and into Manitoba, we see solar energy being a real big player in this kind of landscape. We've already got some big solar plants in this part of the world. So again, the southern parts of Canada are likely to produce pretty significant solar power. I'll kind of fly through the next couple slides, but in terms of potential in Canada, we have hydroelectric in the east, hydroelectric in the west, and again, this solar and wind idea in the kind of central provinces in Canada. So, and there's enough, in British Columbia, most of the electricity, actually almost all of the electricity is driven by hydroelectric generation. So there is potential to do this across Canada. And in terms of the urban environment, really there's been a lot of work looking at kind of how we build urban centers. Urban centers are great places to promote sustainability, promote innovation, and promote this kind of idea around equity. So good examples are across Canada, we've implemented all sorts of technologies, like things like green roofs to solar panels on roofs to different types of building design that you guys will talk about today. And these technologies, just powering large buildings is a massive undertaking, but it's also a massive effect on the climate. So I would encourage, I guess, Gord will chat about this, but I would encourage this group to look at those types of innovative strategies, especially in urban centers. And that's right.
Hey, Gord, just before you come on, there's been a request to have the presenters' audio on for one attendee. We're going to make you a co-presenter so you can enable your video. Okay. We're going to try that at least. So just give that a minute. I think Kaylee's doing that as we speak. And maybe you could try. Gord, working? No?
Yep, we're giving it a try here.
Great presentation, Ryan, just while we're trying to enact that.
Okay,
Thank you very much. Okay, over to you, Gord. Thank you.
So now we're going to shift, we're going to shift gears to building resiliency. Ryan has set the table to explain what is happening to the Earth as climate changes. And we're going to talk a little bit about the effects of climate change on buildings. We're going to, just a sec here. I can't, oh, there we go. A little bit of a lag here. Just go back here. So today can everyone see my screen? Apparently they cannot.
Nope, can see your screen fine, Gord. It's okay. We're hoping to try and get you to be visible, but that's not, doesn't look like going to happen. So just carry on. Thank you.
Okay. So today's presentation is going to cover the difference between sustainability and building resilience. We're going to talk a little bit about what owners are doing to inform themselves of what the risks are from climate change to their buildings. We'll cover very, very quickly the major drivers in the economy around infrastructure risk. And then we're going to finish the presentation by giving you examples of design strategies for achieving resilience at the building scale. And then we'll summarize the presentation. So at Pinchin, we look at resilience in this way. If you can create durability and add sustainability, you will achieve resilience. Some examples where resilience and sustainability actually cross over one another. Both sustainable design and resilient design involves multiple energy sources. It involves the use of reclaimed or recycled water. There's some aspects of disaster fortitude design. Both look at passive systems and reduced environmental effects. We are both concerned about floodplain evaluation, and then other aspects including sourcing local materials, having access to transportation and indoor environmental quality. So this is where resilient design and sustainable design are similar. Now we're going to go into a section where we're going to talk a little bit about work that is being done and the process by which this work is being done to assess infrastructure risk with respect to climate change. Infrastructure risk assessments follow a number of different protocols. Pinchin uses the PIEVC protocol, which is endorsed by the Climate Risk Institute. Other similar standards include the ASTM Guide for Climate Resiliency, the CSA Guide for Durability in Buildings, and ISO 31000. These internationally recognized standards are done in conjunction with BOMA BEST, or work in conjunction with BOMA BEST, GRESB, Fitwell, IRM, LEED, and Climate Lens. So what's the PIEVC protocol look like? The PIEVC protocol was first enacted in Canada in about 2004 in conjunction with the Government of Canada and Engineers Canada, and they created a protocol. And the protocol looks something like this. In the first step, we look at the definition of the project. Why are we interested in assessing infrastructure risk for a given site? Then we gather data and look at the climate modeling for that given geographic area. So this is where Ryan MacDonald's work comes in. He applies climate science and tells us a little bit about what the future climate might be for that given geographic site. We apply that information to the infrastructure components. So basically, now that we know that we may be in an area with increased wildfire or increased drought or increased flooding, we can now look at the infrastructure through that lens and apply some engineering logic to the assessment. So we create a risk assessment from that. Sometimes we apply engineering analysis if the risk assessment points out some high or extreme risks. So under engineering analysis, you're basically testing the capacity of an infrastructure system against what the future capacity might need to be. So for instance, you might determine what the current volume of water that can flow into roof drains might be with the available drains and size of drains that you have. If in the future the intensity of rainfall is going to be greater, then we want to test and do some analysis to see if the current drain capacity on your building will be sufficient to handle the additional volume or the intensity of rainfall. That would be an example of engineering analysis that could be done. And then a report is provided with conclusions and recommendations. These reports can also be married to a second phase, which is called multi-factor analysis. And this is where we involve community and societal interests, and we call this the triple bottom line. So this is the PIEVC protocol. Infrastructure risk involves climate and weather trending. It looks at all of the various base building infrastructure systems, which are listed here on your screen, and we gather this together to create a report. One of the other aspects of the protocol is to establish with the client their risk appetite. Risk appetite is basically what are they willing to accept as risk given different scores around their vulnerability and risk for climate change. So generally, this is defined by their level of insurance and how much they're going to have to pay out if an extreme event happens. So again, we sit down with the client at the beginning of the project and we establish their risk appetite based on what the climate modeling is going to say. A large component of the risk assessment involves creating a heat map for determining the climate risk. So how do we do this? On the bottom scale, you see probability. Probability is also known as likelihood. On the left-hand side, you see severity, also known as consequence. Probability is a value that is derived from the climate modeling that Ryan and colleagues do. So for instance, Ryan might suggest that in the future, there are going to be many more high degree days that need to be contended with in consecutive order. So for instance, in the area of Montreal, Quebec, we might experience in the next 20 years a period of time where we will have plus 32 degree temperature over a 3-week period. The probability of that is quite high. So Ryan might assign a score of 4, and then we would, as engineers, examine the infrastructure based on what the climate science is saying and determine that if we had heat stress of the sort that Ryan is considering to be a high probability, we might assign a severity score to the cladding of 4. We multiply 4 and 4 together and we get 16. So that is called a medium risk. The way this scoring works is anything that falls into the yellow, and obviously the red cells are things that we want to look at for further examination and possible recommendations for adaptation measures. So this is what it looks like in a report. You take all of the infrastructure systems and you apply a risk score to those items following the model I provided previously. And once you do this for every infrastructure system, you start to see very graphically a pattern emerge, and it allows the assessors comprised of engineers and other subject matter experts to zero in on things that they should be be spending time on in terms of working with the client and that particular building infrastructure. Let's talk a little bit about what's driving infrastructure risk assessment in Canada, over and above the obvious, which is climate change. What is driving these assessments in our country? The first one is environmental, social, and corporate governance. So as pension fund managers, as investor groups around the world apply greater levels of measurement to their investment partners, one of the things that they're also looking at is the environment and climate change. So using internationally recognized benchmarking tools like GRESB, there's a component of GRESB, this ESG benchmarking survey that is done that involves climate change. And what building owners and investment partners, building developers have to do is demonstrate to their ESG partners and advisors that they have considered or are considering climate change in their future developments or their current buildings. So this is a large driver of why building owners and portfolio managers and property managers across Canada are now becoming interested in arming themselves with the information that they need around what future climate change might do to their infrastructure. The second major driver is the rising cost of insurance. John opened the presentation up with some information. The bottom line is the insurance industry is several years ahead of everyone else in understanding climate risk and the threat of climate change to infrastructure. And on that basis, they are mitigating against what they're seeing in their modeling by raising insurance premiums. Some of these premiums are getting to the point where building owners are having difficulty operating their businesses. So one of the mechanisms that building owners can use to try to have a better conversation with their insurance providers is by arming themselves with a infrastructure risk assessment report, so that they can demonstrate to their insurers that they are aware of what the given risks might be to their particular building and what they're planning to do to mitigate against climate change. That might enable them to reduce their insurance premium. The implementation of adaptive measures is essentially, once the report is done, it becomes a design and construction project like any other. So we've now gone through the assessment. We understand what the potential risks are to a given piece of infrastructure. Within reason, changes might be offered, such as redesigning the roof to make the roof stronger, looking at different solutions for capturing and storing rainwater on the site, and so on. So a design is created for those adaptations. Those are tendered, and we have construction to follow. So at this point, now that we've understand what the particular things are that are required for the building, we can implement those through traditional methods. At this point of the presentation, we want to shift again and talk a little bit about what the design community is doing in response to climate change. So we want to talk a little bit now about how to achieve resilience at the building scale. So these are different design strategies that are being introduced throughout different parts of the world already, and you may see more of this in North America and Canada in particular, as we have a greater understanding of climate change risk. So one of the first strategies is designing and constructing or retrofitting buildings to handle severe storms, flooding, wildfire, and such. So this example on the screen is from a village in the Philippines in an area that is highly susceptible to hurricanes. So it's clear to see that the shape of the individual dwellings and the positioning of the dwellings has been the orientation has been arranged such that this type of design should better withstand the effects of hurricane winds and hurricane storms. Locating critical systems to withstand extreme weather seems fairly obvious. So moving critical and susceptible infrastructure components away from where the weather might be most extreme, or to provide protection. Modeling design solutions based on future climatic conditions as much as possible. All of this today is about understanding that climate continues to change. So we cannot design for what has traditionally been the case with weather and climate. This is an example from 2018 where the Lower Mainland, one of the Vancouver Coastal Health Regions put out an RFP for engineers where they were asking the engineers to run the energy model using a weather file presentative of projected 2050 climate conditions, i.e. they wanted the mechanical engineers to try to design for what the weather could be in 2050 as opposed to what the code required it to be in 2018. We want to create buildings that will maintain livable conditions in the event of extended loss of power or heating fuel through energy load reductions. So we call this passive survivability measures. So creating designs that will allow the building to remain habitable during extreme weather and changes, whether that is in the wintertime or in the summertime, and introducing passive measures that can help us create that survivability. We also want to create durable buildings using such features as rain screen details, windows resistant to hurricane winds, and interior finishes that can dry without needing replacement. We want to use low carbon input materials and systems such as wood, bamboo, and other low energy input masonry. We want to create beautiful buildings that will be loved and maintained. What we're talking about this morning is not creating a bunch of concrete pillboxes that can be buried in the earth where nobody's going to be really happy living in these buildings. We can still achieve beautiful design and make buildings livable and beautiful by introducing some different ways of thinking. We want to reduce dependence on complex building controls and systems, providing manual overrides in case of malfunction or temporary power outages. So, simple example of having a well. Now, not everyone's going to be able to have a well in their backyard. We grant you that, but the concept is to reduce as much as possible dependence on complex building controls. We want to optimize the use of on-site renewable energy. So here's some examples, and designing for high energy efficiency, including passive solar heating. So the example of the PV panels in the backyard, where we're not only gathering energy from the sun to power our own home, but also contributing to the grid. And on the right, by designing the building in such a way that we are using the sun's energy and introducing passive solar heating to reduce our dependence on fossil fuel. We want to design buildings for maximum daylighting. So the shape of the building will be instrumental for primary source of lighting in the future. So the orientation of windows, the shape of the buildings, to take advantage of greater daylighting is going to be very, very important as we move through the future. We want to carry out water conservation practices and rely on annually replenished water sources, including harvesting rainwater as the primary backup water supply. So a couple of examples of how we're harvesting rainwater. One of the ideas that I'm particularly interested in is the concept of a blue roof. For people who are in the roofing industry and building envelope specialists, they will probably cringe a little bit at the idea that we want to create a reservoir on top of a building. But this concept is not a new concept. In fact, in the 60s and 70s, we used to encourage water to collect on top of buildings to promote air conditioning or cooler climate during the summer inside buildings. In this concept, it recognizes that the additional load of high intense rainfall might not be handled well by existing municipal stormwater systems. So the need to try to collect and store safely the added rainfall volume on sites like the roof or elsewhere on the site becomes of greater interest and importance. So this is an example of a blue roof design that is designed in such a way that we've got a strong structure that can tolerate the additional live load. We've got a waterproofing system that will allow the water to be stored safely without leaking into the building. And we have a way to use that water that's been collected to somewhere else on site or in other systems, or to safely drain it into the municipal stormwater system. We want to provide redundant water supplies, and we want to consider water storage that can gravity feed to the building. Here in Alberta, where I live, we have still have examples of water towers like you see in the right, which are basically gravity fed systems. And the island of Manhattan, if you look at several of the apartment buildings, the older apartment buildings, you'll see wooden reservoirs on top of buildings that are essentially gravity fed systems, reservoirs that will continue to function when there's a loss of electrical power. Obviously, we want to consider options for human waste disposal, composting toilets and waterless urinals. We want to design for use of local materials, available products and skill sets. An example here being the Richmond Olympic Oval, which took advantage of a lot of timber in the structural design of the roofing. And timber is a locally and abundantly available material in British Columbia, so this would be a good example for you. We also want to specify products and materials that will not off-gas or leach in the event of flooding or fire. I want to design with that in mind. This is an example of how we've had to adapt to climate change in existing designs. This is a school modular classroom, a portable, if you will. And the portables have been on this school site in central Alberta for about 8 to 10 years. But only in the last 3 years has the school division had to contend with annual frost heaving and soil change. So every spring for the last 3 years, the skirting around the base of these modular classrooms is becoming damaged from frost heaving. So the solution is, it's not likely that this is going to stop anytime soon. So the solution is to provide what we'll call a slip joint to allow the skirting to adapt to the rising and falling of the frost within the soil around the base of these buildings. Use of fire-resistant cladding materials. Quite obviously, if we can improve fire resistance on the outside skin, that's going to help the occupants survive longer, particularly in areas where wildfire is a greater likelihood. In Fort McMurray, we had in the wildfire that occurred back a few years ago, 25% of the infrastructure burned, but 75% did not. But many of the buildings that did not burn could not be safely reoccupied because they were contaminated with wildfire smoke particulate. So we encourage the use of better grades of filtration and at the outside plane of the building. So basically, if we can lock down the air handling system during wildfire events, it's likely that we will have less of an issue with contamination of our ductwork. Use of fire-resistant and fastened roofing materials. Examples from the southern United States and places like Florida tell us that different styles of roofing, particularly in areas where we experience tornadic winds, hurricanes, and other such extreme weather, we need roofing systems that are going to be able to withstand these effects in a better way. So metal roofs and fastened roofs in general are gaining more favor in places like this. We also want to borrow from the past. The ancient designers knew how to create air conditioning and comfort without the use of mechanical systems. So using and adopting passive cooling strategies in our buildings and designs. An example of that is a simple transom window that allows airflow into the home without introducing a lot of mechanical control. We see examples of this on commercial buildings as well. The Manitoba Hydro building is in the cutaway on the right, and it involves many different forms of passive ventilation. We want to protect critical infrastructure within the building. This is a design institute in California. Obviously, the design accepts that there may be flooding, so there's nothing critical on the ground level, and all of the mechanical and important electrical systems are embedded in concrete ductwork that's well inboard of the exterior envelope. Using hurricane and seismic connections in typically non-hurricane or seismic locations. For pennies on the dollar, we can improve and make more resilient wood frame construction by introducing simple concepts like hurricane clips. So it doesn't cost a lot of money. Considering different shapes, so the image at the left is of a school in Tornado Alley in Oklahoma, and it's understood that schools become the focal point for the community during emergency events. And so the shape and design of the schools becomes ever more critical, especially when you're contending with tornadic winds. The other way to deal with it is put everything underground. So there are many examples of below grade applications that we can point to that will help make people survive better and buildings infrastructure survive better in places where tornadoes and hurricanes are prevalent. We can also elevate for flood protection. Seems obvious. The image to the right is an example of a building on stilts, or actually both are, but there are examples now where buildings can be provided with a hydraulic lift. So in the event of rising floodplain or rising water levels, the building can be elevated above the rising water and then be brought back down once the threat has passed and the water has dissipated around the site. So elevating for flood protection and allowing buildings to be elevated in response to high water levels is a solution that is now available. Or you can just design for a floating home. We've got examples throughout Canada in communities in Victoria and Vancouver and even in Yellowknife where homes are designed to float. And so this is a real opportunity, particularly as floodplain, as we understand greater about where flooding is going to take place in Canada. So our journey map to resiliency at Pinchin is as follows. We understand that there's a risk from climatic exposure. We then apply a vulnerability assessment to that infrastructure to understand better where the risks really are. Once we understand the risks, we can design mitigation and adaptation measures. And then it's important that we not only commission what we've done, but also train the occupants on what we've done. And then because climate continues to change, in a few years, we'll need to re-audit. So that is our journey map to resiliency. And that is our presentation. So thank you for listening.
Thank you, Gord. Thank you, Ryan. Both excellent, thought-provoking presentations. I enjoyed them both immensely. A couple of questions from the audience. We're kind of a bit, we're past our hour, but people are welcome to stay on if they want to keep listening. Question, do your calculations take into account, this is for you, Ryan, the naturally occurring cycle of the sun between solar minimums and solar maximums? We're in the throes of a century-class event according to NASA on spaceweather.com. I don't hear much conversation around that cycle, somewhat similar to, but not as severe as the Maunder minimum from 1645 to 1715. I had to admit I had to Google that. Ryan, any thoughts on that?
Yeah, so general circulation models, or GCMs, account for what they're trying to do is simulate the energy balance of Earth. So they do take into account these longer term cycles, and they do I guess, try to take into account all of the relevant physical processes in the Earth's atmosphere. So the short answer to that is yes. The long answer is, relatively speaking, the physics of, the effects of long-term. So long-term variability is always there. What we've done, but in terms of the physical environment now, is we've exceeded that kind of that long-term variability. So we've amplified the system, and we still see that long-term variability playing out, but it's dwarfed by this anthropogenic effect. Hopefully that answers your question.
Okay, thank you very much. Gord, question for you. Clearly, watching this, there's two main aspects. You design newer buildings to be climate conscious or mitigation conscious, but clearly we're going to be adapting existing buildings to be climate conscious. Do you have a sense of where the best short-term value will be? The people on this call will be saying, where do I begin? The assessment's the place to begin, clearly. Are there areas of mitigation that we get good short-term value for? And that may be an unfair question. The obvious one to me is drainage. You can enhance your drainage, you cut the risk of flooding. Are there other areas that you see as being, or roofing? You change the roof, you make it more hurricane resistant. Are there other areas of mitigation that give good short-term bang for buck in mitigation?
What my colleague Ryan is teaching me from his climate modeling is, in Canada, the #1 threat to our building infrastructure will be from what we call heat stress. So that might surprise people. They might say, gee, I live in an area where we've had ice storms, or I live I live in Toronto and I hear that we're in a floodplain area. So flooding might be a bigger concern to me. But as we live in the Northern Hemisphere, the #1 threat that I'm seeing, and Ryan can challenge me on this at any point, is heat stress. So what does that mean? It means that we need to be more conscious of how we're going to maintain livability inside our buildings, particularly in the event of the grid going down. So imagine living in a high-rise apartment during a period when the temperature is going to be plus 32 degrees for 15 straight days, which is a likelihood in the next 30 years in certain parts of Canada. So mechanical systems, air handling systems, are currently not necessarily designed for that kind of load. But further to that, we want to create backup systems inside the building that will allow the air conditioning and the air handling to continue to operate when the grid goes down. So good opportunities are to incorporate some sort of passive renewable energy. So using solar panels and then storing the energy in smart batteries and having that power available to run critical systems like air conditioning and elevators during periods when the grid goes down. So there's a long-winded explanation for you, John.
Okay, thank you, Gord. Thank you. No, that's yeah, clearly a big, somewhat intractable issue. Okay, we're over our hour, and I do see some people dropping off, but good number of you. Some good feedback from the audience, Ryan and Gord. So thank you very much for that. Just a couple of closing comments. We will be posting this. A few questions. Will we post this? Yes, we will. This will be on our website in a few days, so people that want to view it afterwards can do so, or share that link with your colleagues. We will be continuing this series with other series as part of our practice innovation series. And you will be getting a survey, people that attended. So give us your honest feedback. We want to prepare these and present these as a service to all of you. So if there are topics we can expand on in the future, we'll try and do that. And in closing, many thanks to Ryan and to Gord, our speakers. Thanks to Kaylee and Rui in the background making this happen. And thanks to all of you for being part of this journey with us. We're all learning this together, and we look forward to interacting with you excuse me, as we move through this situation together. Thank you all. Closing off. Have a good day.